Okay, we'll get started. So I've posted the homework assignment onto CCLE, but there is a mistake in the last section of the file. Okay, so if you can download it now, you don't have to. You can wait till the corrected version is up, but it's quite long. But there's the last section that says PCA on real data, okay, and I have a few mistakes in some of these parts, so I will fix that and I will get that uploaded. Everything above PCA on real data is fine and good to go. You'll need to have these three packages installed on your machine. So that's MVT norm for multivariate normal distributions, ggplot, which I think most of you already have, and then the real data or the real application will use this package called Chemo Spec, which is chemical spectroscopy analysis. Okay, and so maybe I'll just briefly show kind of the use of principal component analysis on data from Chemo Spec, and then I'll introduce our next topic, which will be some optimization stuff. Okay, so this will kind of wrap up our section on principal component analysis. So I'm still working on writing this, quote, midterm exam. And so I'm thinking it'll still be take home. I'm thinking there'll also be a handwritten section, okay? So there'll be, is that weird?
Will it not be take home?
Yeah, I guess because it's handwritten, like it could be an in-class thing, and it would probably just be some basic things like see if you can make the covariance matrix by hand. If I give you a small data set, right, like 4 or 5 data points, can you make the covariance matrix by hand? Can you do a eigen decomposition by hand on the covariance matrix? Okay, you're shaking your head. And I think, like, we don't do that anymore, right? We've got computers to do this stuff for us. But I think there's still a little bit of instructional merit in having a little bit of to do stuff by hand, okay? But I'll let it be take home, okay? Which means you can go on the internet and say, how do I do eigen decomposition by hand? And it'll show you, okay? Just don't cheat, right? Like don't talk to each other about your answers. That's all I ask, okay? I feel like I'm being nice to you guys, so be respectful of that, I guess. Okay, let's take a look at this Chemo Spec thing. It's like whenever we hear chemo, it sounds like chemotherapy, so it sounds terrible. But the chemo part, it just means like chemical based. Okay, so when we're talking about chemotherapy as a treatment for cancer, it's basically they're loading your body up with these chemicals that are fighting cancer. So unfortunately, I don't know about unfortunately, but just like that word chemo has now become associated, certain things just become associated with the thing that it's most well known for. But okay, let's load up. So if you don't have it, you're gonna have to load up Chemo Spec, and then I forgot what the data set is called. Let me data SR. Yeah, okay. Whoops. Okay. Chemo Spec SRE data. What's it called? Okay, SRE.IR. Okay. So I do data. Oh, there it is. Okay. Okay, so I'm loading up SRE.IR, which is our which is the data set we're going to use. Okay, and then when we look at it, it says list of 9. Okay, this is infrared spectroscopy data. Okay, so I don't know if you guys took chemistry, and if you guys kind of remember if you ever had to do like a spectroscopy lab. So basically, you put a sample of some kind of compound into this machine, and then the machine bombards the compound with different wavelengths of light. Okay, or in this case, infrared light. Okay, or it's called infrared light, right? I don't know. And then the compound, depending on its chemical properties, will absorb certain wavelengths, okay, and it will not absorb other wavelengths, okay. And so you'll get this thing where it's like, hey, it absorbed this wavelength, and it absorbed this wavelength, and whatever, okay. And so you can, if you're a chemist, you can look at this data and say, oh, this is what we're seeing here, okay? I'm not a chemist, so I have just minimal knowledge about how to analyze this kind of stuff, but it serves as a good tool in kind of seeing an application of PCA, okay? So we're going to look at this. We're going to ask for the structure of this SRE IR data, okay? And we see that it's a list of 9, okay? So the first thing is a frequency, all right? These are actually, I think they're called wave numbers, okay? So it's the inverse of the wavelength, yeah, okay? And then the data itself is in this, we can see it's a matrix with 16 rows and 1,800 columns, okay? So and essentially this is spectroscopy data on 16 different samples of this oil, okay? And I guess we can ask for the help on SRE.IR, see what it says. It's a collection of 14 IR spectra of essential oil extracted from palm, whatever this, and saw palmetto. Okay, so something used to treat BPH in men. What is BPH? I don't know. Something. Okay. All right. Anyway, we're looking at this. Okay, and then it also contains 2 additional spectra. One is evening primrose oil, and then the other is olive oil. Okay. Is there a difference between the spectra of these 14 samples? So I guess they went to different stores that sell this stuff. Okay, and then they're looking at are these saw palmetto oils, saw palmetto oil extracts, are they similar for all of these 14 different brands? And then, hey, are they ripping us off? Are they, we're going to check it against olive oil and see like that, stuff like that, okay? All right, and so here, this is essentially all of the different wavelengths, and then over here, this tells us the absorption at a particular wavelength, okay? All right, and so, and then everything else is just kind of the labels of these things. And so we have, let me just cheat and look at my the commands that I used to do the plotting here. Plot Spectra is the command, okay? And so this library, Chemo Spec, has a function called Plot Spectra, and we can just say, hey, plot spectra, and then you specify which one you want plotted. So I'm going to just say plot the first one, okay? And so here this, I don't know if you guys remember your days from chemistry class. This looks like well, it is spectroscopy data, okay? And so we can see, at this wave number there was this much absorption and this like this, okay? All right, let's plot another one, okay? And that looks quite similar. What about this one, okay? And they all look kind of similar. We can kind of compare like one to another. And like, is there much difference from here to here, okay? Or from here to here. So from this one to this one, it looks like it's like the same shape. Maybe this one absorbed a little bit more at kind of the same places. This one, the next one though, the shape changes a little bit, okay? Can you guys see that? The next one, the shape changes a tiny bit. All right, and then we can plot all of these. I can say which 1 through 16, and they're going to plot them all right here, and it's kind of hard to see what's going on, but we see, there's certain shapes that are quite common, and then, there's some discrepancy in this area, some discrepancy in this area, okay? We can add an option that says offset is equal to something like 0.3, and what that does is I'm going to have to set my Y range. Okay. And so what this does is, rather than plotting them right on top of each other, they offset them a tiny bit, okay? And so when we look at this, we see, okay, there's a few things that stand out, okay? This one, the olive oil, which is this top one here, yeah, it does look different from the other spectroscopy graphs, okay? And so does the evening primrose oil. But hey, so does this one, this PSRE, and some of these, okay? Like for example, if we look at the second versus the third one, GNC versus ET, whatever this is, okay? We see, hey, this peak is a little bit taller here, and over here, this peak is a little bit taller here. I don't know if you guys can see that here. Yeah? Okay, so we can kind of say like, all right, let's do a principal component analysis on this, okay? So, and this is where I messed up in the homework. I forgot to center this data matrix, okay? So, that's a rookie mistake here. So what we're going to do is we're going to take this SRE data, okay, and I'm just going to make a copy of it just so I can deal with this, all right? And then I'm going to I'm going to just take the extract out the this data matrix, this 16 by 1800 data matrix, okay? So here I've got a matrix. I can just say class SRE data, and we can see that it's a matrix and thing like that. And so so we can perform PCA on this, okay? So what I first need to do is I need to subtract off the column means. There's 1800, over 1800 column means. So I got to find column means of SRE data, okay? And I'm going to store this as my kind of centering information. Okay? And then I want to subtract off all of these, all of this centering information. So how would I do that? How do I subtract off? So I've got, so I would transpose our data matrix, right? And then I would subtract off the centering. And then this result, I transpose back. Does that make sense? Because R, when you perform operations on a matrix, it kind of goes column-wise, all right? So if we want to subtract off the column means, which is effectively a row of vectors, we got to transpose it, subtract off basically column-wise, and then we got to transpose it back. Okay, and so this should work, I hope. So I'm going to, and just to kind of check, I'm going to just call this, I don't know, I got to come up with some good. So we'll call it SRE data C to indicate that it's been centered. Okay, and then so we can just ask. So we'll look at the centering info. Oh gosh, there's a lot. Okay, I forgot 1800. I shouldn't have done that. Okay, so we can ask for our SRE data centered. Okay, and we can ask, hey, what are the column means of this thing, SRE data C? Okay, but it's gonna say they're all 0. Okay, so we can just kind of say, you know, all dot equal 0 in this thing. Oh no, I messed something up. Okay, let's see.
Wait, why would we do that?
Because I just want to see if the column means of our centered data is indeed 0, right? Because if I've subtracted the column means from it, so maybe I did this wrong. Let's just ask for the column means. Maybe I screwed up. Let me see. Column means of this, let's ask for the first 5. They look like they're 0.
Very close.
Yeah. They look like they're 0. I mean, it's e to the negative 18. You're not going to get anything. It's within machine. Do I not use all equal to check if they're all equal to 0? All equals 0 in this? Oh, you know what? Maybe I have to, oh, the lengths differ, so I have to repeat 0 5 times. Okay, yes. So we're okay. Okay, so I just got to do, I'm sorry. So I'm going to just create a vector of 1868 zeros, and I'm going to say, hey, are all column means of this centered data matrix equal to 0? And it says yes. Okay, at least within machine error tolerance. Okay, and so we can this centering data kind of gives us an idea of the average wavelength of all of these, right? Like if we averaged all of these together, we would see the centering thing. So I can just say plot centering info, okay, and I would just say type is equal to L. And so this is kind of like the average. This is like the baseline, okay? So if we averaged all of the other so if I averaged all of these lines together, okay? So if I averaged all of these together, what I would end up getting is pretty much this, is what we're saying, okay? Because we've centered it. Okay, and then so now I can perform PCA on our centered data, okay? And so for that, I'm gonna do singular value decomposition, okay? And so singular value decomposition decomposes any matrix. It doesn't have to, so eigenvalue decomposition must work on square matrices, diagonalizable square matrices, and SVD can work on rectangular ones. And so the result of it will be three matrices, which we're going to call U, sigma, and V, and we're going to say do the SVD of our SRE data, centered data, okay? And then so now I can say, hey, what is, we can just say, what are the dimensions? How many eigenvalues did you get? It gave us 16. What are the dimensions of each of these things? Dim USV $. So we have our U matrix, which is a 16 by 16 square, and our V matrix, which contains our kind of our eigenvectors, 1868 rows, okay? And so our V matrix contains our eigenvectors, and so we can just kind of look at the, the first and the second principal components, or even just the first, and this maximizes the difference from curve to curve, okay? So I can say, hey, let's look at, so that we're doing all of this kind of this manual principal component analysis, right? So I could say, let's look at this V matrix. So when you do singular value decomposition, it decomposes, let me just pull this up here. It decomposes the matrix into 3 parts, and that V matrix at the end is essentially your principal directions, okay? And when you project your data onto this V matrix, then you get that's the principal component analysis, okay? So you have U sigma V. So we're going to just say, hey, I want to just see this first column here, okay? This is essentially our first principal direction or first principal component. We just have to project our data onto this. And let's, I'm going to plot this, okay? So I'm going to plot PC1 type equal to L, all right? And then we see this funny looking graph, okay? This is what maximizes the difference from curve to curve, okay? So basically, maybe I can, how do I screenshot this? Not screenshot. Let's copy to clipboard. And maybe I can create a PowerPoint. We don't really use PowerPoint, but but here we go. Okay, so I'm gonna just throw this in here. So I want to show the kind of the baseline graph, and maybe we'll see this. Okay, so this is our first principal component. How do I get this in here? Is this working? Okay. And then let's look at this one. Okay, so this is our baseline. Copy to PDF. Okay, copy plot. Okay, so what we're saying is, let's take a look at kind of, how do our plots differ from each other? Okay, so let's look at our U matrix, USV $U. Okay, and we'll just look at the first column here. Okay, and we'll also look at and just for a reminder, we'll do our spectral plot. Where's my command? Spec plot spectra. Okay, and I just want to kind of highlight the difference between Spectra 2 and Spectra 3. Okay, so we're going to just take a look at these ones. So with Spectra 2, let's all right. Oh, that's better, I think. Maybe this is too big. All right. And This is Spectra 3. Oops. Okay, so let me kind of show you. So if we look at the kind of the coefficients that are being applied to our first principle direction, okay, in our PCA analysis. So this is the baseline, right? This is kind of the average of all of these. And then it says, hey, if you want to produce this one, okay, which looks a little bit different from this one, okay? So kind of look at our baseline, look at this, and what do we see? We see in the baseline these two peaks are kind of this far apart, and over here the difference between this peak and this peak is more pronounced, right? Okay, and then over here the difference between this peak and this peak is just the opposite. Okay, so this one is lower and this one is taller. Okay, so let's look at that. We see there's a sharp contrast between something here and something here. Okay, and so what we see is that when we look at kind of the second curve and the third curve, we see the second curve, it says add a negative version of the first principle component, and then the second one says add a positive version of the first principle component, okay? And does that make sense? Yeah, so this is our baseline. Our first principle component says basically lower this peak and increase this peak over here, okay? And so to go from here to here, we're actually going the opposite direction. And so for that second one, it says add a negative version of that, which means basically increase this peak and decrease this peak. And that's so you're gonna, it's basically, so this thing says, hey, take your baseline and add a slightly negative version of this, and you'll get this, okay? Meanwhile, the third graph says, yeah, take that baseline graph and add this, meaning decrease the peak of this one and increase the peak of this one, okay? Which is what we've got here. Decrease over here, increase over here, and you get, and it highlights kind of the difference between these spectral decompositions here, or not spectral, what am I talking about? Spectroscopy data, okay? And so we can kind of break apart, and so whereas before, you know, we had 16 different curves, and you can look at this, and unless you're an expert, you're just kind of like, oh yeah, they look kind of like little wavy little things, right? And you might say like, oh yeah, there's, you know, if I'm looking at the second one and the third one, you know, there's some difference here, okay? And so, you know, and that's just using the first principle component. Using the first principle component only, you know, how much of the variance are we capturing, okay? And so this is, that's basically kind of what we're getting at. And so, you know, to see how much of the variance we're capturing, we can look at the eigenvalues, which show up in D, okay? And so we can see, oh, you know what? Oh, wait, am I doing this right? I'm trying to remember if I leave this or if I square it. Or square root them. Okay. So with singular value decomposition, see there's all these, so with the singular values are the square roots of the lambdas. So I think I square them? But now I'm confused. Okay. All right, well, we can get an idea, and I think I square these. Oh gosh. I'm not sure. So I want to say this is what I'm supposed to do, and that the first component alone captures about 89% of the variation. That that maximizes, and then the next one adds an additional kind of 4%. And so, we can look at each of these components. Okay. Does this make sense? Is this? So this is an application of PCA, right? I think sometimes you guys ask, when are we going to use this? And so if you have, multivariate data, and a lot of it looks kind of similar, PCA will highlight kind of the differences from one observation to another. Okay. That took longer than I expected. I was going to introduce the gradient-based optimization. I guess we'll save that till next week. So anyway, your homework assignment is posted online. The first parts are kind of performing principal component analysis using the rudimentary functions in R. And what I mean by rudimentary functions are you just ask R to do eigen decomposition, or you ask R to do singular value decomposition. And I'm thinking as part of your take-home exam, I will force you to do even more rudimentary work in doing the eigen decomposition manually yourself. But when it's take-home and you got the computer, you can always say, ask R to do the eigen decomposition and check your work, right? So you'll be evaluated on the work that you show for that. So you can do. So you'll go through the process of doing kind of this principal component analysis. I've tried to highlight the difference between performing PCA using the covariance matrix, the correlation matrix, and singular value decomposition. What's the difference between these three PCA methods? And then so after I feel like, covering those topics, then you're basically going to do this kind of analysis on this spectroscopy data, okay? And I just have to fix a few things in there because I forgot to subtract out the means. Okay. All right. Do we have any questions about stuff? Yes.
Won't be enough principal components. It won't be appropriate for this data set. Because the first one covers 89% of the variation.
Yeah, so you might be able to say one of them, one is enough.
So let's say if the data is the one previous, would you go up to?
Yeah, you'd probably want to go up to, I don't know, there's a rule of thumb, right? So around 85%, 90%, that's pretty good. Generally, there's a huge drop-off between the amount of variation captured by the principal components. So yeah, I think with singular value decomposition, you got to square them to get the variance components, and then with eigen decomposition, you can just leave them as is. But I'll just double check. On that before I state that as fact. Okay. They're all very related, and it's easy to get confused. Okay. All right. Well, we'll end there then, and I'll just update the homework assignment. You should be able to get started. It's long. There's a lot of reading, but in terms of the actual stuff that you have to do, it shouldn't be too crazy hard. Okay. And then as always, there's Piazza, so if you're getting stuck on anything, you can go on there and talk.